This will pretty much wrap up the classification part. So pretty much the only other point to be said here, without going into too much, like I said, theory of the support vector machine, because that will take a long time to sort of go through. The point to be said here is that so I just want to go to the support vector machine function, and just to show you where the kernel basically shows up. Okay, so as I said, without I'm skipping a lot of stuff, but at the end of the day, this is what the support vector machine objective actually looks like. So basically, this notion of taking the slack terms and all that sort of thing. So let me just backtrack for a minute. So this is what the actual objective looks like. So the margin, these psi I terms, these are the slack. Okay, these are the slack variables. So the slack variable basically tell you the distance of that point from the hyperplane, like I said. So you basically want to minimize that. So if things are misclassified, you want to basically shrink that. You want to have a small value for the slack. And this is the margin term. So, and basically put this as a minimization problem to have so remember I said that you want to maximize the margin, but the margin is 1 over W. Okay, so you want to maximize that. To maximize that, you have to minimize W, right? So that's why I put, so what you do is that you say if you want to maximize this, you might as well, minimize this. So the equivalent conditions, right? So to maximize 1 over W is the same as minimizing W itself. But see, W is a length, and it is a square root of the, W1 squared, W2 squared, so in a normal Euclidean. And square root is a bad thing, okay, when you want to do optimization. So instead of doing this, we say, actually there's no problem, why don't we just do W squared? Because minimizing W is the same as minimizing W squared. So that's how this shows up. And we put the half here so that, this is pretty much coming from the way we optimize these problems, we take the derivative. So when you take the derivative of a square, it becomes 2 times that, and so, the 2 times will basically cancel out with that 2. So we want to get rid of extra, terms. So that's why this pretty much boils down to the margin term. Okay. So this is pretty much the same as maximizing the margin, because the margin is actually this, and by maximizing this minimizing this term, we maximize the margin. So that's the margin term, and this is the whole slack thing. And then there is some constraint that that they come out of the geometry of the problem. But you don't solve this problem. This is called the primal, the primary objective, or the primal form. You actually solve the dual problem, and the dual problem you can rewrite this. And again, I'm not going to go into the theory of this. But the thing I want to mention is that the dual problem, it only involves finding these alphas. Okay, so you have to come up with a alpha 1, alpha 2, alpha n. These are called these values. These are the coefficients. You have to basically figure those out. But this is the key point, that we only need the kernel matrix. Okay, so to any of this, only the kernel matrix is required between any 2 points. So as long as you can give me the kernel matrix, this is just, this turns out to be a convex optimization problem. So I can pretty much globally, and there's only one unique optimal solution. Okay, so I can pretty much run the method. Any simple method will do. I can just run, for those of you who are familiar, you can do just gradient descent. Okay, gradient descent is the simplest optimization method you can think of. You simply, it's like saying that if if I want to find the lowest, the minimum solution, start anywhere in the space. So in this case, the problem is known to be convex. That means the objective kind of looks like this. So it doesn't really matter where you start. Okay, just pick a solution at random. That means, for example, start here, and just go down the hill. Eventually, you'll get to the optimal solution. Okay, you might take you a long time possibly, but you'll always find the optimal. So, I mean, there are many faster methods, but I'm just saying that this problem is actually a nice problem. It's a quadratic convex problem, optimization problem. It's quadratic because you have alpha I times alpha j. Okay, you need to find the alpha value, and so it's quadratic in the alphas. So you can just do gradient descent or something else, but the point is you just need to know the kernel value. So basically now we can take a graph, we can compute the, based on the labeled points, I can compute the support vector hyperplane, and then any new point comes in, you just plug it into the hyperplane equation, and you figure out whether you are less than 0, more than 0. That way you will be negative or positive plus. So it actually becomes very easy to classify things from that point on. Okay, so that essentially wraps up the classification of graphs. And so are there any questions? Because I'm going to start something different from. So any questions on the classification stuff we did yesterday or today?
Sir, what does it mean by pair-wise classification?
Pair-wise classification. So that's probably you mean when you have more than one, when you have more than two classes.
Yes, sir.
Okay, so yeah. So supposing you want to do support vector machines, and you have three classes, right? How do you do it? So if you have three classes, the problem is that the hyperplane is a binary split. Okay, that's all a hyperplane can do for you. A hyperplane will never split the data into three parts, right? So if you have three classes, then what you have to do is, you say, okay, here are my, class 1, class 1, class 1, some class 2, class 2, class 2, class 2, class 2, class 2, 3, whatever. So maybe you put the 3s here. So if you had data like this, right, there are three classes. So there are support vector machines can only find hyperplanes. So there are two main ways of doing it. Okay, the one is called one versus the rest. So one approach is you do one versus the rest. So in this case, you have to learn three classifiers, right? Class 1 versus everyone else, class 2 versus everyone else, class 3 versus everyone else. So it will give you three hyperplanes. So class 1 versus everyone else would be maybe something like this. Class 2 versus everyone else might give you something like this, and class 3 versus someone else might give you a classifier like that. Right? Now the only thing you have to be worried about when you do the intersection of three hyperplanes is what happens in this region, right? Because now, so there's a little bit more work to do to clean it up, so to speak. Okay. So here you have to. So this is clear, right? So anything on the left of this. So if you look at the boundaries, actually again this is basically hyperplane 1 versus rest, right? So this is H1. So everything on the right is H1, everything on the left is everything else. This is the 2, and then finally this was the H3. So if a new point comes in, so supposing a new point comes in here, what is the class of that point? Well, you try H1. H1 says it can be, it's on the 1 region, right? H3 tells it's in the H3 region. So now it's a question between, and then this 3 is 3 versus 1, so you'll probably classify it as 3, right? So the region for that point is that with respect to 3, you are in the third region. But actually, you don't know that. So it also depends on the. Let's see. How would you? Yeah, this is actually an ambiguous region. So actually, we know for a fact that this region is definitely for 1, right? So no matter which hyperplane I choose, that's well-defined. So for other regions, I guess you have to do voting or something like that. You can look at the distance, right? So if you're here, you have to say how far am I from this, how far am I from that. And you might choose 3 over 1 because you're further away.
Probability.
Yeah, exactly. So in this, a support vector machine gives you a distance, it doesn't give you probability. Okay. So you have to see the separation from the hyperplane. Okay, so how far are you removed from that? So this is the one versus. So you have this kind of situation that you have to handle. This is a very naive approach. I'm sure they have much more sophisticated ways of doing this. So, but there is a whole well-defined. People have studied this and they've come up with alternative schemes. The one I just showed you is like the simplest possible thing that I can think of right now. All right. Any other questions? If you're on the hyperplane, then you can classify them either way. You type just random. Yeah, I mean that a point that is on the hyperplane, and if 2 points are from different classes, what that means is that that is probably highly unlikely to happen unless they're like exactly collinear, right? I mean the point is that because the hyperplane will try to minimize slack. Right?
It can be possible that the points on that.
Oh yeah, that can happen. Yeah, the points can be. I mean, but you know what that means, right? If a point is on the hyperplane, that means 2 classes are very close to it. That means you're really that narrow of a margin. So that's highly unlikely again, because if you have many other points or many other things, it doesn't really matter for these guys, because the margin will take care of that, and the slack will take care of that. So in other words, you're really squeezing the margin. If you don't really, so the point is that if you don't care about the margin, then it can happen. But if you try to maximize the margin, then you're going to have more. But in any case, I think if a point is on the hyperplane, the answer is you choose one or the other. Okay, you either choose from one class, randomly you can choose. Or you can say, I don't know. Don't classify. If it really, and if it happens a lot, then you have to do something else.
Sir, can there be a situation where we have a heterogeneous feature space? And if that case arises, what to do?
Heterogeneous feature space. What do you mean by heterogeneous feature space?
Say for example, at the end, one end we have graphs and other side we have only nodes or vertices.
Okay.
So that's a heterogeneous feature space in that case. Does that scenario ever arises?
You mean the input space?
Yes.
So remember the feature space is the kernel space, right?
Yes.
That is whatever you've done. If you really had an input where you had a graph and a bunch of points and things, you define the similarity whichever way you want to define it. Once you've defined that similarity, the feature space is just any standard feature space. Any other questions? Okay, so now we're ready to switch gears to. So I want to sort of show you some. So basically talking about scale. So I'm going to talk about distributed graph mining. Okay, so there's a lot of recent work on large-scale machine learning, big data sets, right? Big data. And so today I'm going to be talking primarily about using distributed computation for pattern discovery. Okay, so I'm going to focus on pattern discovery first, but I'll also mention PageRank and some of the other methods. So obviously we all know the big revolution in distributed systems. So distributed systems are actually studied; they have been studied for a very long time in the context of high performance computing, so scientific computing and other supercomputers. So this was obviously the state of affairs, let's say, till the PCs came about and everyone started having their own very powerful desktops and machines. So then after that, it was basically cluster computing, okay, a cluster of heterogeneous networks. Okay, just connect a bunch of machines, and then we use this thing called the message passing interface, okay, MPI. There's another thing called PVM, parallel virtual machine, to basically connect a bunch of machines and program them with explicit message passing. So what you have to do is that whenever you have to, you have an algorithm, some machine is doing one thing, another machine is doing another thing, and you need to obviously sometimes communicate information between two machines. You have to explicitly bundle up the message, send the message over the network, other machine gets it, and then there are all issues of synchronization, because certain computations require input from all the different sources before you can begin the next step. So that was the state of affairs. And now the problem was that on the one hand you had these very powerful supercomputers, right? In the supercomputer you also program the same way. You use the message passing interface. The difference is that in a supercomputer you have a very fast interconnection network. Okay, so you can actually communicate much faster between the nodes. And then if you just have a cluster of machines, then obviously you're communicating over whatever backbone, internet or Ethernet backbone you have. So it's much slower compared to a supercomputer. But the programming paradigm is more or less the same. You just do message passing interface. The cost trade-offs are different. So then in the 2000s, right? Now the whole point was that if you really wanted to program the system, high performance computing or like a supercomputer or a cluster, the entire burden was on you. Okay, you had to do all the computation, you had to do all the message passing, you had to do all the fault tolerance, right? So imagine in a big thing, something failed, you send a message to some other node, the node basically, imagine a cluster of 1,000 machines. Disks are failing all the time, the machine basically hangs up. Your entire computation is gone because you're just waiting for that one node to respond to you. So Google, so this now we enter basically the web era, right? So in the web era, you've got huge amounts of data. Of course, you've got lots of computational resources. And so Google said that if you keep on doing this by hand each and every time, it takes too much effort and too much work. So they came up with this notion of MapReduce. So the MapReduce was a very, very simple paradigm, which basically said that if you have a distributed computation, all you have to do is think of it as basically key value, pairs. So you've got some data, okay, and you have some hash key or something like that, and you can assign the data to different nodes via some basically a mapping function. Okay, so use that key to basically map the data to the different nodes. So it could be as simple as a hash function, and basically someone gets, all these nodes get the value, and they do something on that, and then there is some sort of a reduction operation. Sometimes you have to aggregate, the values together. Now, what they said is that you are going to program only using this paradigm, okay? Map and reduce, map and reduce, map and reduce. So any computation you can do this way. What they will provide, the system provides you everything else, okay? All the message passing, all the fault tolerance. If a node fails, it will automatically squash that computation, restart that computation somewhere else. So suddenly it became much easier to program these very large clusters of machines. Right? So now I can actually not worry about whether I have a 1 machine or 1,000 machines or 100,000 machines. The system and the backend will do my job for me. I just have to think of what is the basic computation I want to do. Okay, how do I map my tasks, and how do I do some reduction, like computing some aggregations. Right? So the simplest example, like the hello world of MapReduce, is the word count. Now you take a text document, And all you have to do is you have to basically, each word becomes a key, okay, with a value of 1. And you just hash these words onto the entire distributed. So imagine you have 1,000 machines. You have a bunch of text documents. You simply extract all the words from every document and you simply hash on that word. Now, right, a machine will get so the same word will go to the same machine, right, because you're doing the hashing, and it's getting a value of 1 from multiple input sources. So you'll just do a reduce. It'll basically do a reduction operation on that, and you get your word counts. So you just do map reduce and you can count it. So this becomes now, map reduce with Google's, proprietary stuff. So people came up with Hadoop. So Hadoop was the open source, Java map reduce framework. It used the Hadoop file system. So there are a lot of, aspects to this. There's sort of the distributed systems aspect to it, right? There's the fault tolerant aspect to it. But we'll be living in the algorithmic space, because I'm not really going to be talking about the actual system level issues. Those are very important, but we are interested mainly from the point of application, right? So I want to run a data mining job. I want to write a data mining algorithm. So how do I do this on a relatively large, let's say, cluster? So let's look at that, and in the context of graph mining. So the situation that, this is just, I'm just going to skip these slides because I took it from somewhere else. So this is our, So let me actually backtrack and talk about two, again, So remember I am right now interested in frequent subgraph mining, and then we can talk about other problems shortly. But let's say I want to do frequent subgraph mining in a distributed manner. So this is distributed. Okay, this is the problem I want to solve. So it's the same question that we had before. You have the two scenarios. You have on the one hand a database of many graphs. So here's the database, G1, G2, Gn. And then you have the single G, a very large G versus a database of graphs. So let me talk about the first one first, because this is actually relatively easy to do. When you have this situation where you have many graphs, right? And I'm assuming you have millions and millions of these graphs, right? So you have a minimum support value, and you're supposed to basically figure out what are the frequent patterns. So how should you do it? Well, the distributed system, it has basically got a bunch of machines, right? So let's just call it machine number 1, machine number 2, machine number P. So you have P compute nodes, okay? Different clusters, different machines. So the best strategy is that you take your data set and you just divide it into equally, at random, into P parts. Okay, so basically start out with a distributed data set. So take each of these and just split it. So this will get D1, this will get D2, this will get D2. Okay, so I'm just doing, you can do round robin or you can do something else if you want, but essentially the idea is to equally partition the input graphs into these smaller chunks. And now what I can do is, each one of them, I can extract, okay, so now there are several strategies. So now my data set has been split up among these, so of course, processor 2 or node number 2 doesn't have access to D1, right? So only the graphs that are assigned to this particular node, it will only have those. So the idea here now is that I must do something locally, but then to get the global frequency, I have to do aggregation, right? So this, I'm not really yet thinking about MapReduce yet, but I'm just giving you the general overview of how you're going to basically proceed. This distributed stuff will actually happen under the hood. If you had a Hadoop-like system, you're not going to explicitly control, who gets what partition. You let the system sort of partition it, and you're going to do operations based on that. But here I sort of, we can start out with this assumption first, where I explicitly assign, if I can control where the data is placed. It's like saying that this machine, this data is local to that machine, meaning it's on the local disk or something like that, so I can access it very quickly. If you don't have that, let's say you had a distributed file system, then you can just assign to that node. You can say you're responsible for graph 1, for graph 3, graph 10, whatever. You just have to get the IDs, and this node will basically request the underlying file system to give it those graphs on demand as it needs. Okay? So either way, whether you start out with that assumption, we'll just assume that you have this data access available to you. Whether it's on the local disk or it's on a distributed file system, that's not the important point. Right? We just assign them some graphs that they are responsible for. Okay, so now it doesn't really matter whether it's a Hadoop system or a supercomputer or whatever. This problem we can do regardless of making those assumptions. Conceptually, it's the same situation. This is an easier problem because I just have to know how many graphs contain my pattern, right? So now think of the pattern that I have to enumerate. So what normally one does in this case is you first do all the single edges, right? So everyone pretty much computes from their local graph the frequency of all the single edges. So this guy is going to give me, so I'm going to call that F1. This one will also compute F1. This one will also compute F1. But actually this is F1 of 1, F1 of 2, F1 of 3. So F1 means, the subscript is the size, right? So I'm computing all the single edges, and the superscript tells me which partition the edges belong to. So this is actually easy, right? So this gives me, so for example, take the AB edge, right? So supposing there's an AB edge, this guy will say this happens 5 times. In this case, the AB edge, happens 2 times. In this, the AB happens 0 times. That means it does not even report it. Okay, so the edge AB never happens. Doesn't really matter. Once you have done this local computation, you can do a reduction. Reduce on all edges. Right? So you don't have to do just one. You can do the entire level at a time. So just do a reduction operation, that is sum them up, and then you'll get the global frequency. So it's actually as simple as that. Essentially, all you have to do is, every time you pick a pattern, so in this case, they're counting all the edges, right? To begin with, everyone counts all the edges, and then they do a reduction to get the global support. And once you get the global support, you prune the infrequent pattern, and you say, now these are the valid patterns for the next level. So the computation is going to go in an incremental manner. So let me write out these steps. So the idea is that step number 1, processor, or let's just say compute node I, basically will find the local support of all candidates. So initially this will be all the single edges. So we'll say all the candidates of size, in this case is 2 vertices. Anyway, size k. So you're given the. So actually, what does that mean? Sorry. Let me backtrack. I'll just do this in a recursive manner. So we'll assume that you're given. So step 0 is that. Actually, let's just change this. So step 1 is given f of k. Okay. The set of frequent patterns of size k. Okay. Second is so compute node I finds the local support of all candidates of size k plus 1. Okay, so the idea is that you take a frequent pattern, you extend it locally, right? So you add one more edge in your partition, in your set of graphs, and see, what extensions you can find. and every machine is doing the same thing in parallel. So everyone is basically starting out with this thing, and this is like a breadth file, a breadth for a search, a level-wise search. You do single edges, you do 2 edges, 3 edges, 4 edges, and you keep on proceeding. So you just extend them and you come. Okay, so you find the local support. Step 3 is basically do a reduction operation. Right, the summation is an example of a reduction operation. You can do max, you can do min, anything that, those are all part of a generic term we use, reduction. Okay, reduction basically means compute some aggregate function, sum, max, min, but in this case it will be the sum. So reduction, or in this case the summation operation. Okay, so basically do reduction operation across all compute nodes to determine global support. So global support is a true support, okay, across all the partitions, because in this case there is no problem. If I just add them up, I'll know the global support numbers and you can just find out. And then you prune the infrequent ones and then you basically go back to, so this basically gives you f of k plus 1. Right? So from the candidates, the ones that are really frequent, they give you the next level and then you basically go back. Keep on repeating this till no new patterns are found. So this kind of a computation is very easy to do in MapReduce because pretty much the operation itself, gives you that ability. So, I did this in the context of, assigning the data and partitioning it that way. The other option would be you simply, use a map function, okay, to map, to map all the edges, so to speak, among the compute nodes. You can say you're responsible for computing this one, you're responsible for computing that one, and then the reduce operation will take all these values and simply sum them up. So it's pretty much like word count in that sense. Once I know the pattern, and the space of all the patterns is essentially a word count type of a problem. So essentially, instead of a word, I have a pattern. So that would be one way of implementing this, breadth first search. There are many other sort of variations one can do to optimize this computation. But this is the basic paradigm. Just keep on doing this, and you have your solution. Now, the way you can improve this is that there is one issue that you can probably think of, which is when you're computing the local support, it turns out that you might end up computing many things that do not turn out to be globally frequent. So there might be a gap between things that are locally frequent and things that are globally frequent. Okay, so maybe there's one really bad partition where just because of the way you partition the data, a lot of the things turn out to be frequent. Everyone else is saying they're not frequent, but this partition says it is frequent. That means you have to exchange a lot of messages, right? So when you do this reduction, everyone has to do an all-to-all, right? This is pretty much an all-to-all communication. You have to exchange the complete support count. You have to send it pretty much to everyone else, if you will, because there's no centralized node. Okay? In a distributed system, we're not doing any centralized computation. So how can I know the global support values? The idea would be I get messages from everyone else, and I can do a reduction on my own node, for example. Or you can let the whole distributed system do the reduction on its own. But in any case, a lot of messages are going back and forth. And so every time there's a gap between the local support and the global support, you're going to have computational, issues. And because of the way we're partitioning, we cannot control this beforehand. So this can happen that certain partitions give you many more locally frequent things, but after the reduction, they turn out to be not, frequent. So then you can see, okay, how can I improve that? So there's a lot of work, basically around this, how to optimize the local part. The global part, there's not much to be done. I mean, you have to do the reduction. Sometimes you may be able to guess that something is going to be frequent, and you might avoid, doing the reduction. But generally, the optimizations come from, how to distribute the data and to do the local support. So this is, I think, one of the basic ways of doing so this is actually the easy problem. As I said, this is not really that challenging. I mean, and there are solutions already, many people have talked about the multiple graph situation, and they have had MPI-based implementation, MapReduce-based implementations, and so on, but they all follow generally this basic paradigm. And so, but one thing to be noted here is that this is more or less a BFS search. And in general, this is basically in keeping with MapReduce. Basically, you're saying that each phase, each level, is kind of like a map and a reduce. Okay, and so this sort of is easy to implement on a MapReduce type of a framework. If you want to do a depth first search, then it's much harder, and maybe in a MapReduce it's almost infeasible to do a depth first type of a computation. Depth first would mean pick a pattern and just keep on expanding that pattern. But there's like too much effort you're doing only for one pattern, right? So generally you want to leverage the computation across different patterns to really keep the distributed system busy. So the only way to do depth first would be if you can distribute the pattern in such a way that multiple nodes are exploring multiple depth first paths at the same time. But then there's the issue of load balancing. Okay, what happens is that you don't know which path will lead to frequent pattern. And so it can happen that only one node keeps on expanding something, it can keep on finding new things. Some other node has expanded its branches, and it turns out that there's nothing. So basically what I'm saying is that when you look at the computation of frequent subgraphs, what happens is that you have the situation where you start with the empty with the empty graph. Initially you got a bunch of single edge patterns that you need to count, right? Okay, and then you successively so one idea, like you said, you just go level by level, right? So go level by level. So this is level 2, level 3, level 4, based on the number of nodes. Actually it should be number of edges. So level 1, so 1 edge, 2 edge, 3 edge, and so on. So this, as I said, is very, very amenable to MapReduce because it sort of falls in that same paradigm. But if you want to go depth first, that means one node picks this up and it tries to expand the tree under that node. Okay? The other guy picks this up, but the tree under this might be very small. The tree under this might be even smaller. The tree under this might be huge. So the problem is that if you try to do this in a depth first manner and you say, I'm going to distribute the work, the problem is that if you just do a naive sort of distribution, if one node gets this, it has to do a lot of work, whereas this node and this node, they're basically sitting idle. Okay? Because beforehand you don't know which branch will turn out to be frequent. And so then your only option then is to actually do dynamic load balancing. Sort of work stealing or work donation, all kinds of strategies. So if these guys become idle very quickly, so this is basically processor 1, processor 2, processor 3, processor 4. 2 and 3 basically are done and they're just sitting idle doing nothing. To keep the system in full utilization, you have to then say, this guy is somewhere in the tree. It has to sort of take this and then break this into chunks, and then assign them to those nodes. So the idea then is that you have to do, but this is much more complex because now there's a whole, and MapReduce will not do this for you. Okay, this is something you have to do because this is a computational logic. MapReduce doesn't know anything about the computational logic. It just says as long as you can give me a map job and a reduce job, I'll keep on doing it. But this kind of load balancing is not what MapReduce does. I mean, it does load balancing in the sense that the entire map phase is distributed equally, and then the reduction will happen in parallel. That's the only thing the Hadoop thing will do for you. So this is still your responsibility, right? So it becomes, it's not that suitable really for a MapReduce type of, so you're not really leveraging that framework to the fullest extent. So that's why you'll see very rarely someone doing a depth first search because it's much more complex to do that. So it's mainly breadth first because you can simply map it to the MapReduce type of computation. And pattern mining is a quintessential MapReduce problem, right? Because essentially you have a bunch of patterns to count, and the counting is the reduction part. So you simply let everyone do all the work in parallel. Okay, so that's the single, the multiple graph scenario. So let's focus on this part actually. This is the more challenging task. How do we mine a single graph? And so I have to still enumerate things. And now, the moment you go to a single graph, you can immediately see the trouble. The trouble is that if you want to do the same thing, you have to now partition the graph first. So there's only one graph and you have to partition it. And unfortunately, once you partition the graph, you get into this notion of false negatives. That means there's an edge that crosses partition, and a frequent pattern relies on that edge. Okay? So if you really partition it, that edge is lost, because it's neither in this partition nor in that partition. So how to, then the issue becomes how to tackle the edges that cross between partitions. So suddenly things get a lot more complex. But let's see how we can do some we can do something. So okay, first I'm going to outline some alternative paradigms. So first of all, for the time being, let's not worry about partitioning the graph. Okay, so let's make our life simple. I'll say the data will not be partitioned. Okay, so you want a single large graph. So I'll say that a given G, and I need to find out the frequent subgraph. But let's assume the entire G I can access from any given compute node. Okay, so I'm assuming that G is relatively small, or at least it can fit in the main memory of all the compute nodes. Okay, so I've got, of course, the same situation as before. There are multiple nodes, P1, P2, and so on, or rather 1, 2, and 3, 1 through. So there are multiple nodes. The graph is pretty much residing locally. So you're just replicating the graph on every computer. They can access any edge, any vertex, and they can figure out the frequencies and so on. So the graph is available to you locally. Now this will become a problem if I have a really huge graph and it doesn't fit in the main memory of every node, right? So for example, if you have a Facebook type of a network, it has about 1 billion nodes and I don't know, 10 billion edges or something like that. So that is going to require hundreds of gigs of memory to store. Okay, because when you store the graph, you have to have the pointers and so on and so forth. So the memory blows up. So you need an extremely large memory cluster to handle that, to really handle that. Otherwise, you have to split the graph. So for now, we are assuming that if you have a machine like 8 gig, 32 gig, whatever, you can still do reasonably large graphs. So every graph can be put in there. So now let's talk a little bit about the existing paradigm. So there are these graph libraries. Pregel is again Google's graph mining or graph algorithm platform. There are things called Giraffe. There is I'm going further down my. Let me see where is it. Oh yeah. So this I'll come back to the slide again. But you have these things like GraphX. GraphX is built on top of Apache Spark. Okay, so Spark is another one of these distributed systems that lets you do many machine learning tasks and other things on a distributed platform. And they do memory-based computation. Okay, so they do in-memory things, so they're much faster than let's say Hadoop. So right now there's a battle going on between Hadoop versus Spark. So basically Spark, you can think of it as a successor to Hadoop. It can basically handle anything that Hadoop does, and it can give you some optimization in terms of the memory and so on. So there's a big, sort of impetus around doing things under Spark. So nevertheless, GraphX is the sort of the graph library on top of Spark. So you can say I'm going to use an existing graph package, which will allow me to compute adjacencies and things like that. And why not just use that for my basic computations? For the Hadoop, there is Giraffe. Okay, so Giraffe is a Hadoop-based graph library that will let me do kind of graph computations. And then the third one is GraphLab, which is also very popular. Again, this is like machine learning over graph-like data. So these are the three sort of things we want to look at. But all three systems they are in this paradigm called think like a vertex. So this is where they make, so again remember the task here is, you can do all these graph computations on your own. You can do them by hand, take the graph, replicate it, partition it, okay, and some algorithm you want to implement. Basically now you write the algorithm, and you use message passing or something else to basically communicate. Again, it will not be fault tolerant, it will not be this, it will not be that. So Google came up with this, again, this system called Pregel. Okay, the Pregel was one of the early ones, where they proposed this notion of think like a vertex. And so the idea is that, and then all these successor systems like Graph and Giraffe, GraphX, Giraffe, they follow the same computational paradigm. So the paradigm is think like a vertex. So any computation that you can do, where it only requires local information. Okay, so you are so think of a vertex in the graph, and if you're thinking like a vertex, what is the only thing you have access to? The only thing you have access to is your neighbors. That's it. So you've got maybe incoming neighbors, outgoing neighbors, and any computation you can do just using that vertex-centric approach. These systems make it extremely easy to program them. So basically the idea is that you take a large graph and you basically take this entire graph and the system will handle for you the computation distribution among the nodes. You don't explicitly control that. You just say, here's my graph, I have 100 nodes, okay, this graph is large and I want to compute some operation on this graph. And you just define this function. What is the function f that you want to compute on that node? Okay? And then the system will take care of doing this computation, and because it's a vertex-centric, this goes in this paradigm of bulk synchronous programming. That what happens is that basically all these systems, Pregel, GraphX, Giraffe, they implement this paradigm that there are steps, there are multiple steps to the computation, okay? And each time, the only operation that's happening in each step, it's called a global, like a super step, is that every node gets a message from its neighbors, okay, every node. So in a completely distributed manner, this node will get messages from its neighbors, this will get messages from its neighbors, this node will get messages from its neighbors, entirely in a distributed manner, in parallel. Everyone gets an input message, like all the incoming information. It computes some new state or some new value, and then it basically pushes it out to its neighbors. Right? So every step is all that's happening. You get information, you compute something, you push it out. And so you can think of this, basically the graph is changing state from one state to the next, to the next, to the next. And the system is handling everything for you. If some node fails, meaning, this node may have been assigned to some compute node, under the hood. This node fails, then the system will migrate that computation to some other node automatically. So you do not have to worry about anything, in terms of the physical system side of things. You just give this function and you're done. Okay, so again, the same sort of philosophy as MapReduce. Now, remember, MapReduce is not applicable or not really useful for every computation, but where it maps very well, it saves you the headache of managing everything on your own. Same thing here, that this is not going to be able to solve all the problems, but any computation that requires only local information, it can do for you. And you don't have to worry about how to distribute, how to load balance, right? Because it's automatically load balanced. Because this computation you're doing is generally not very complex, but you're doing this on a very large graph, right? On a Facebook scale network, and the system will migrate, on failures, it will do a completely distributed job. So let's see which tasks are easy to do. So for example, this kind of think like a vertex is extremely useful for shortest paths, because all you have to do is, here's a small, actually, where's my graph? I forgot to put the graph, so let's skip this. Let's go to PageRank. So PageRank is actually much easier, because PageRank is something that these methods optimize to do PageRank. And as we were discussing yesterday, how does Google actually do this? obviously they are doing this in a highly distributed manner. And so this is like a Pregel-like system or a thing like a vertex, a vertex-centric system is ideally suited to PageRank, because what does the PageRank do? At any given point in time, right, the PageRank value essentially is take all the incoming weights, right, proportional to the degree. So this guy is going to contribute to that one, proportional to the degree of this, meaning or inversely proportional to the degree. So you take the weight, divide by the degree, take the weight, divide by the degree, map it here. So in each super step, right, this bulk synchronous programming super step, you basically get incoming nodes. So this is just what the local computation at each step is. You just add them up and then send the PageRank value to everyone else. So it's extremely, now you basically get PageRank for free. I mean, there's nothing more to be done. Just get, your only function is you look at all incoming edges, take all the PageRank values from those, add them up, and basically send them on your outgoing edges. So you just write that code, and then distributing the entire PageRank computation across the whole network will be handled automatically for you. So you can use Giraffe, you can use GraphX, you can use all those things, and you're done. Shortest path is the same actually. Shortest path you just have to compute, from your incoming thing, you look at what was the shortest path before, right? And now when you follow this edge, you just add the value on that edge, and then you take a minimum. And so as long as you keep on doing the minimum each time, so the computation, instead of a summation, it becomes like a minimum type of a computation. So look at all incoming edges, okay? Look at all the paths up to that point, and then take the minimum and then add one more and push it up. So shortest path and all these. So many methods in regular sort of structural analysis, centrality computations, they're actually very easy to implement on these kinds of distributed systems. But the problem happens with the graph mining part. Okay, so we have to look at that issue. So I think we need to stop, right? So I think this is a good place to stop, because this says that basically the stuff that we did on the structural analysis, shortest paths, distances, average path length, diameter computation, PageRank values, other types of centrality, hits and all those methods, you can actually now solve them, fairly easily. I'm not saying the most efficiently, but they're fairly efficient. So they're both easy and efficient for those kinds of computations. There may be some issues when you scale up very, very large, but essentially those can be done. So in the next lecture tomorrow would be, I guess, how to do a single graph mining. How would you do it on a vertex-centric approach? So this would be a good mental exercise. If I can only do vertex-centric operations, can I actually extract frequent subgraphs? Let's see what ideas you have, and then we'll discuss them tomorrow. Okay? Thank you.
Try to come by 12 in 20 minutes. Right.